what I want to do in some senses is explore a few more physical aspects of chemical equilibrium. If I can get this. Why is this so ugly? There we go. Just to appreciate a few subtleties about equilibrium. There's not that much new that you can learn about. Now, what we could do is think about equilibrium in more complex environments. So, for instance, in the past, I've talked about electrochemistry, or ionic solutions, or something called activities. It's a quantitative analysis. You probably learn about activities. Or maybe it's an instrumental. I can't remember. But it's one of those two classes.
Quantitative.
Thank you, quantitative. So not everyone has taken that, but soon your people in front of you in forensic science will be starting new students. Yeah, it's not a required course for forensic science. So I don't really like to cover those things because I don't find them to be particularly interesting or engaging or particularly enlightening. They're just kind of extensions of the stuff we learned. And I think if you understand the fundamentals of equilibrium, it's pretty easy to apply it to other situations. So what I want to do is I want to use equilibrium as a jumping ground into more interesting things. And the thing is that chemical equilibrium, of course, is so important in chemistry because of the name. But also because, systems equilibrate. Chemistry is an equilibrium process. And so it's important to know what you see at equilibrium and then start to think a little bit about the process underlying that, the microscopic details of the system. And I want to, in particular, one thing that I want to look at in particular as kind of motivate our discussion is in the end is to realize what we're going to realize is that when we talk about chemical equilibrium, we don't have any specification for how long it takes for something to equilibrate. In fact, we just set time to go to infinity. So there's no sense in the speed at which something reaches equilibrium. And I think that there's so much more interesting information about the speed. Because a great example of this, and we'll see multiple examples over the next two lectures, of reactions where delta G and our conditions seem very, very favorable for some process to occur, and yet it doesn't occur. So it's almost as if we're missing some sort of additional factor, right? I can get an equilibrium constant, get a delta G. Looks like it's product favored. I go mix things together in the lab and I sit there and nothing happens. Happens all the time. The important distinction there, thing that we in some sense missed in that discussion, we haven't really discussed how long it should take for something to reach equilibrium. And there is in some sense no limit to that. I mean, obviously it's going to be a reaction dependent thing. Some reactions are very quick. For instance, you put sodium chloride in water and it dissolves, that reaches equilibrium extremely rapidly at any temperature. You know that happens very, very fast. But again, if you mix oxygen and gasoline together in a tank and let it sit there at 300 Kelvin, 1 bar, calculate delta G for that process. And like every combustion reaction in mankind, delta G is negative for combustion. It's very exothermic, very entropically favorable. Delta G is always negative for combustion. But yet, gas doesn't spontaneously combust. It would take us thousands and millions of years for that to reach equilibrium. And that's the important distinction there, that thousands and millions of years it takes. There's a temporal quality to equilibrium that we haven't appreciated, that things take time. And therefore, our diagnostic for chemical equilibrium between ones that are very, very effective and ones that are not effective is some measurement of time. But of course, that's kinetics. And we're going to see that kinetics and equilibrium are one and the same. They are in some sense measuring the same things, but from two different perspectives. Equilibrium thinks about concentrations at infinite time. When the system is done, And that it's equally likely for it to go forward as backwards. That's what chemical equilibrium is. The microscopic reversibility kicks in. And that's the dominating feature. That forward and backwards are at equal rates. There are obviously reactions where they don't go at all. And so if we can quantify that speed, we can learn something about the process itself. It's much deeper than just what happens at the end. We can understand what happens in the middle. I think that's much more interesting. We're going to learn a lot more about processes and chemical reactions by analyzing, in some sense, how the system in time traverses across equilibrium. And so I kind of want to get out of equilibria as quickly as possible so that we can go to that more meaningful information. Something that we can learn a lot about. And so when we get to kinetics, we're going to spend like 3 weeks in kinetics. We're going to spend a lot of time in kinetics because there are so many ways we can use kinetics to learn about chemical processes that involve equilibrium, may not involve equilibrium. And there's just much more interesting chemistry going. We can consider time. So that's where we're headed for. So what I have left is I just want to talk about equilibria just a little bit longer. I want to think about, last class we talked about how equilibria, in some sense for gases, depend on pressures. And we're going to look at a really great example of that on Tuesday. The last lecture of equilibrium. Really great example where pressure and temperature dependence plays a huge role in the chemical equilibrium process. And so we'll look at that example next time. But I want to, so in that light, I want to make sure that we understand how equilibria depend on our parameters, which are temperature, pressure, and concentration. These are 3 parameters of equilibrium: pressure, temperature, and concentration. We know how it works with pressure. We saw that it's a function of how many moles for gases, how many moles are being converted to other moles, how the number of moles are being changed from products to reactants. And there's a pressure dependence associated. So let's think about how equilibrium depends on the other parameters: concentration, and temperature. Think about the other. So just a little bit of math. And then next class, we'll do something that basically has no math at all. I'll tell you a story, an application story. Next class. Kind of close things up. So let's see where I want to get, how I want to set this up. So let's think about the relationship between the equilibrium constant and temperature. We've talked about pressure. Think about temperature. So of course, this question ultimately, in some sense, comes back to a question we asked on last homework, is that because the delta G of a process is equal to minus RT times the log of KQ, really what I'm asking in some sense is not, I mean, how KQ varies with temperature, but really it's about how does delta G vary with temperature? Right? They're going to, in some sense, vary with respect to each other, except there's a negative sign in a log, right? So there's going to be a slight difference in the way that they scale with temperature, but they're intricately related to each other. So they should have, if we understand how delta G scales with temperature, we can figure out how KQ scales with temperature. Right, so what's the easiest way to do this? Well, you can just brute force the answer. You guys looked at this kind of in homework 3. All you would need to do is pick a temperature and calculate delta reaction H and delta S at that temperature. Well, that's really easy. Well, we know how to do that, right? Delta H at some temperature minus delta H at our standard conditions is equal to the integral from the standard temperature to our final temperature of the change in the heat capacities of the material, which is a function of temperature dT. Right? You guys did this last class in the homework, and we know that the entropy as a function of temperature minus the standard entropy is just the same integral, but we just divide Cp by the temperature. Okay, so if we have heat capacities, right, we can calculate the enthalpy at any temperature we want and the entropy at any temperature we want. And therefore, our delta G at any temperature T is just delta H of T minus the temperature times delta S of T. Okay, easy. Right? So that's a pretty straightforward way to do it. Let me show you a way you shouldn't do it, but is a way that everyone does it anyway. So what I've done here, right? What I've done is, and so I can then take this, of course, and then plug it into this equation. And get K and Q from this value. This gives me the K and Q. I'll just write that here, just to click that.
So that's the way we should do it.
Yeah, that's one way to do it.
Oh, okay.
We'll come up with a better way to do it too. But of course, you could do it this way. It's a totally reasonable way to do it. Right. And the equilibrium constant at any temperature is that delta E to that minus delta G over RT. So let's show you the way you shouldn't do it. And I saw some people do this, right? And it's a really on the last homework. It's I haven't turned it back to you. I'm sorry, but I have looked through a good chunk of them already. This is a really, really common mistake, and it works sometimes. We'll see where it doesn't work. Of course, we'll see that like most approximations that you learn in chemistry, they fail. But this is a really, really common mistake. Every year, at least one student, if not more, makes this mistake. So don't do this. Right. Imagine that you have delta reaction of G circle, which is equal to delta reaction of H circle minus T delta S circle, right? So you have some standard enthalpies at your standard conditions and entropies. And then you say, okay, well, if I want to go to a different temperature, did I kill this right now? Right, we'll call it T prime. Right, all you would say is that, well, then that means that delta reaction of G at that temperature T prime is delta reaction H circle minus T prime times delta S circle, right? You just plug the T into the equation for G and you don't change S and H. Right, you can see why that's wrong, because this assumes that S and H don't change with temperature. But you know that not to be true. H and S very much change with temperature. In fact, they are primarily dependent on temperature. So when does this work? Well, the only time that this would work is when, imagine now that the temperature, as the temperature increases, the enthalpy is also increasing. Maybe it's decreasing, I don't know, it's doing something. And the entropy is all, what's that? Go ahead.
We were going to say by the same amount. That's what I was thinking.
Yeah, so right. So the idea would be,
sorry.
No, that's okay. You've got the right answer. So let me just finish the sentence.
Yeah.
So as temperature increases, the enthalpy and the entropies are also changing, right? And they're both changing proportional to the heat capacity. And then when you multiply the entropy by T, this T goes away. And so T times this, in some sense, it's the same as this. But I've made a critical assumption about that. So if that were the case, right, if I could just take this T and plug it into here and cancel this T out inside the integrand, this equation is exactly, T times this equation is exactly the same as this equation. So when H goes up in temperature, T times S goes up by the same amount as well. And so the difference doesn't change between H and TS. Okay, so that's what you're assuming, that in some sense S and H, or sorry, TS and H grow at the same rate as a function of temperature. And so the difference between them is constant. And the T just gets larger, so this term gets bigger. But that doesn't work because the heat capacities are not temperature independent. The assumption is that we can take this T and bring it into the integrand. And it doesn't work like that. So this approximation, just plugging T in and keeping H and S works, but only when the change in T is really small. So if you go try this for water between 298 and 373, delta G, it works great.
Oh.
No, it works pretty good. Because the heat capacity, as you guys saw on the homework, the heat capacity of water is not that temperature dependent as you go from 298 to 373. It's pretty constant. But if you went from 298 to 800 Celsius, or you had some other material that's much more sensitive to temperature in terms of its heat capacity, this fails dramatically. So this is only true for small delta T, right? Just in general. Right? So sometimes you get lucky and it works, but most of the time it doesn't work. It really depends on the system and the behavior of the heat capacity. So, of course, we can avoid all of that by brute forcing, because by calculating the enthalpy and the entropy at any temperature we want, we accounted for the change in the heat capacity in the integral. So this works great, but it's kind of an inconvenient way to do things. And there should be a way to simplify this, because in some sense, the change in enthalpy and the change in entropy, they're proportional to each other, right? They're both proportional to Cp, but entropy has some additional factor there, 1/T. And so these grow at some related rate to each other. Bless you. So there must be some way to relate the two together into a single equation, right? Because they both grow at kind of by the same slope, if you will. The same change. And so we could probably balance them and hold them at the same limits and calculate how the whole system changes together. Instead of thinking how H moves separately of S, let's think about how they move together. So we're just going to let them grow together. And what we'll get is an equation that's much simpler and much more coherent and more compact than just going into Excel and calculating all the heat capacities, all the enthalpies, and all the entropies. Okay? This is how a computer does it. Right? But it's not always that useful for you to do because, for instance, you might not have the luxury for your process, your experiment, your reaction to be able to measure these things. Right? There must be a better way to measure things where we don't have to worry about heat capacities and knowing everything exactly. Let's see if we can come up with something. So let's come up with a third expression. Right? Consider how delta H, delta S grow in a related way. Okay, and we're going to use an expression that I derived a couple of weeks ago, right? That the derivative of Gibbs energy with respect to temperature at constant pressure is equal to minus the entropy. So this is a nice trick, right? It says that the slope of Gibbs with respect to temperature is just proportional to the entropy. So if we knew the entropy, we would never need to calculate the enthalpy, because Gibbs's relationship to T is just proportional to S. Right? So if we know S, we know everything. Right? But S is a hard thing to measure. H, in fact, is a much easier number to measure. It's very easy to measure because you just have to look for heat going in or heat going out. You can use a thermometer for that. So what I can do is this, right? We can assume that the system, as what we're going to assume now is that that we move temperature slowly. So system stays in equilibrium as heat increases. Okay, so what I want to think about is how does Gibbs energy change, right? So that we just don't dump a bunch of energy into the system and make it re-equilibrate each step as we heat. But instead, let's just slowly move the temperature up. And as the temperature slowly moves up, we move it slow enough so that at every temperature point, the system has equilibrium. Okay? So we're just going to slowly adjust the equilibrium and make sure that delta G always stays at 0. That delta G is equal to 0 for the system. So we can always assume that delta G is 0, which means that S is equal to G minus H over T, right? We'll just equate them together. Well, we don't even have to assume delta G is equal to 0 here. Let me just leave that here. It's not even an assumption we need, right? We can always solve this expression. Okay, so I can plug this in now. All right, this is minus S. So G minus H over T. Okay, and I can split this out. The G over T minus H over T. Okay, and I have an ugly equation for you. Because I have the derivative of Gibbs with respect to temperature is equal to, you think of this as dy dx. Dy dx is equal to y over x minus some other variable minus x. Kind of a funky equation. It's not very easy, right? Because eventually what we want to do is calculate Gibbs energy at any temperature, right? So we're going to have to integrate both sides to get delta G. And we have G on both sides of the equation, right? So we need to clean this up a bit. So what I'm going to do is a calculus trick. Right? What I'm going to do is take instead a different derivative. I'm going to think about the derivative instead of G over T with respect to T at constant pressure. Okay, and this is equal to so we have G times 1 over T times d by dt. We need to use the chain rule and the product rule for this. And we can expand this out and show that this is 1 over T dg dp at constant, dg dt, at constant P. That's one derivative. And then we have to take the derivative of 1 over T. It's going to be plus G times the derivative of 1 over T with respect to T at constant pressure. All right, well, this is easy to do. This is just the derivative of 1 over x by x. So that we get a minus sign and we get 1 over T squared. So this is equal to 1 over T dg dt constant P minus G over T squared. Right, I can now clean this up a little bit. This is equal to 1 over T times the derivative of GD dt, constant pressure, minus G over T but I have an expression for G dt over P. It's G minus H over T. So I can bring that in. And we're going to get a nice cleanup here. Notice what happens now. Now when I instead think about how this Gibbs energy divided by temperature variable T, I get an expression now where the G's go away. Yeah, it's only dependent on H. Minus H over T squared. Right, so what this is saying now is that while Gibbs energy with respect to temperature is proportional to S. So if we know the entropy of the system at any temperature, we can calculate the Gibbs energy it is. But sometimes we don't want to do that. So instead, what we think about is the specific Gibbs energy. How much free energy do we have per unit temperature? And then take the derivative of that. And what we find is that that is only dependent on enthalpy. That's a number that we can measure. Right? It's very easy to measure enthalpy with a little bit of calorimetry. Now, to be fair, as you guys saw this rotation, practically calorimetry is not an easy process. But it's certainly one that you can hypothesize to do if everything is set up properly. Something that theoretically should be no problem. Of course, there are lots of ways to do calorimetry. So what can we do with this equation? So let's clean it up a little bit, right? So we have that the derivative of G over T with respect to temperature at constant pressure is equal to minus H over T squared. Right? And so what we can now do is separate this out. We have that the derivative differential G over T, which is something we can integrate, is equal to minus H over T squared dt. Right? And we can integrate this as a function of temperature. So we have the integral from some standard conditions to some final temperature of the derivative of G over T prime. I'm just using primes here as dummy variables. Is equal to minus the integral from T naught to T of H over T squared dt. Right, and of course now, what we're doing now is we're integrating enthalpy with respect to temperature. Now we have choice, right? We can either assume enthalpy is temperature independent. For small differences in T, we know that's good. Or we have to integrate the temperature dependence of enthalpy. So let's look at those two cases. So for small delta T, we can assume delta H is temperature independent. And so what do we get? Well, on the left side, this integrates out to G at our final temperature divided by the final temperature minus G of our standard temperature divided by the standard temperature. That's just the left-hand side. And we can bring out the H, right? H is temperature independent, so it's just a constant equal to minus H over the integral from T naught to T. These need to be dummy variables. Of 1 over T squared prime, dt prime.
What's T prime again?
It's just a dummy variable because I have T in the integrand. I can't really integrate
Right,
over.
okay.
So it's just I just add a prime to make it so it's not confusing. We can call it X if you wanted. Right, and that's an easy integral to do, right? 1 over T squared, the integral of 1 over T is just 1 over minus 1 over T. So this ends up being delta H at our standard conditions, we're going to assume, times 1 over T minus 1 over T circle. So I'll just put this all together. The Gibbs energy at some temperature divided by that temperature is equal to the change in Gibbs energy at the standard conditions divided by the temperature at the standard conditions plus delta H times the difference of 1 over the temperatures. I'm running out of space. Let me do that.
Where did the negative sign go?
But you get a negative sign from this integration.
Oh, okay.
So the negative 2.
Yeah,
So you get a
yeah.
negative sign from the integration and it goes away. So this is equal to, I'll try to write it as small as I can. All right, and there's probably a cleaner way to write this, but I like it this. A nice little feature. Looks good. Okay, so if we can just take our Gibbs energies that we measure from equilibria or whatever, just divided by T, then we can get this nice relationship between Gibbs energy, enthalpy, and temperature. Right? So eventually we have to get the equilibrium constant, so we're going to have to calculate using, delta G is equal to minus RT ln K. We just have to plug this equation in and do some math. We'll do that. But it's not too bad. So again, you get this really nice 1 over T behavior. And if you guys will see when you get back to homework, some of you who attempted the first extra credit problem where you had to calculate the temperature at which the system calculate the temperature at which diamond and graphite are at equilibrium at 1 atmosphere, you end up deriving an equation that just looks like this. Exactly the same. This is 1 over T behavior times what the heat capacity times the change in temperature, which is just the enthalpy. And you find that the only temperature that allows for that to happen is negative, which means that diamond and graphite can't coexist at room temperature bar, 1 bar.
Yeah.
No temperature. But this is what you get. But delta G over T is proportional to 1 over T.
Anybody's after.
Now we haven't now considered though that enthalpy of course is temperature dependent. Right, so then we have to do an integral over the heat capacity. Right, because we're going to have the enthalpy is proportional to the enthalpy is equal to the standard state enthalpy plus the integral of the heat capacity. And so we're going to have to integrate over that and then integrate again. Right, kind of a pain in the butt. Right, but let's not worry about that. Okay, let's just leave with it. Right, so let's take this equation now. Right, and think now. Right, I don't want to go through this process of substituting in my integral for enthalpy here. Let's see if we can simplify things a bit more by instead converting this into equilibrium constants, and then see if we can look at how the equilibrium constant changes with temperature. Maybe we'll find an easier equation that allows us to compute heat capacity implied or to include temperature dependent. Right, it's kind of a pain in the butt there. But let's just hold on to this equation for now that we have. This has a special name. It's called the Gibbs-Helmholtz law. Helmholtz was the German version of Gibbs. Gibbs did all his work here in New Haven and never communicated any of that information to the Europeans until after his death. Helmholtz did all the work in Germany, and he was the star of the Europeans, even though he was technically about 20 or 30 years behind the math that Gibbs had already done. So it's named after both of them because they both derive the expressions for free energy. Gibbs is well known for the free energy equation at constant pressure. Helmholtz is known for the free energy expression at constant temperature, which is actually kind of what you're looking at in the current problem set. So let's go ahead now and think about KEQ. Right? So we have that the derivative of delta G over T with respect to temperature, constant pressure, is equal to minus H over T squared. Right? And now we just need to plug in the delta G is equal to minus RT ln K. Not a hard expression to do, just takes a little bit of algebra. And what you get is that the derivative of the log of the equilibrium constant with respect to T is equal to minus delta H over RT squared. That extra RT comes from the fact that there's an RT in that expression. Okay, and now what we can do is we can say now that the derivative, the differential of the log of K is equal to minus delta H over RT squared times the change in temperature. Right, now we're back to the same thing again, right? We're going to integrate both sides. And we can assume that delta H is temperature dependent or not. Or we can assume that it is and get two different answers. But now I don't have T on the other side anymore, right? I don't have a T over here. So all of my variables are nicely separated. Remember in the previous problem, I have a T on the left side and dt on this side. That makes the calculus a little tricky. You've got to do some implicit differentiation and a bunch of two kinds of things in order to figure it out. But here, by adding another factor of RT next to the level K, I get rid of that factor of T on the left-hand side inside of my differential, and I just have T on the right-hand side. This is much easier to enter. Everything is all put together in a nice place. Okay, so if enthalpy is temperature independent, we just integrate both sides. And what you get is that the log of KEQ at some temperature T minus the log of KEQ at standard conditions is equal to minus delta H of the reaction over R times the difference in the inverse temperatures. Now that's a nice expression. What does this say? Well, if we were to plot the inverse temperature, right, versus the log of the equilibrium constant we observe, right, what do we get? Well, this is a function, right? The slope here, right? 1/t is our variable x. This is our y. So we have a slope here of delta minus delta h over r times our x. So it's a linear function of inverse temperature. So what we would get is a straight line. And the slope of this line is minus delta h over r. Right. Well, here's a really great way to measure enthalpies. Right? You can measure equilibrium constants, right? That's only a function of concentrations. Remember, this is just a function. Well, for gases, it's a function of concentration and perhaps pressure, right? Just some conditions that you have. You got some reaction, right? You go stick it in the mass spec or the GC to look at the products, quantify your products and your reactant position concentrations, how much of stuff you have, calculate KEQ for each temperature, take a line plot, do a linear regression, and voila, you have your input. So here we can connect concentrations to enthalpy directly. So that's another way. In fact, this is the way that 99% of chemists really do measure delta H for their processes, is by doing this equilibrium. Right? It's much easier to measure concentrations using spectroscopy or indicator, some sort of sensing. It's very easy to calculate this number. You do a titration, for instance, right? Titration is a great way to do it. If it's an acid-base equilibrium, titration is the way you do this all the time. Right? And all this is saying is that as a function of temperature, depending on the process, that the amount you have to titrate is linearly proportional to 1 over the temperature. And that slope, how much that titration changes equilibrium changes is proportional to how much that enthalpy is. Of course, this is assuming enthalpy is positive, of course. Of course, it'll be opposite if enthalpy is negative. If enthalpy is negative, we would have a curve that looks like this instead. This is somewhat of an interesting result. What does this tell us about the product versus reactant favoredness of a reaction as a function of temperature? It depends on the enthalpy. Right? Because if the enthalpy is positive, right? So this is increasing 1 over T, or you could say T is increasing backwards. Right? So for an endothermic reaction where enthalpy is positive, the equilibrium is more product favored at higher temperature. And less favored at low T. Meanwhile, an exothermic reaction goes the opposite way. An exothermic reaction is more product favored at low temperature. This is when I'm doing a thesis project with G. Colonna upstairs. G. Colonna is doing a couple of studying the mechanism of a couple of different reactions that they developed in lab Dr. Trillo. And one of the things that G noticed in her reactions is that in order for them to go to completion, she had to drop them down to dry ice acetone temperatures, which is minus 75 Celsius. Dry ice and acetone has a freezing point minus 75. And the reaction goes to completion, works great, but if you run it at room temperature, it doesn't go at all. Right? And we went back and looked at the thermochemistry of that reaction, and that reaction is aggressively exothermic. It's like minus 200 kilojoules per mole. It's a very exothermic reaction, and that necessarily implies that you need to be at low temperature in order for the equilibrium to be product favored. Meanwhile, an endothermic reaction, right? An endothermic reaction requires heat to go through. Right? So it makes sense that it runs better at higher temperatures because it needs the heat. The more heat you have available from the outside, the more effective an endothermic process is, and the more product favor it will become. So I'll just write that here, endothermic. Reactions prefer low temperature. And exothermic prefer high. Oh, sorry, I have that wrong. Sorry, I apologize. Well, that's really nice, right? A nice little feature of our system. Well, now let's think a little bit, just very briefly, about what if the heat capacity is temperature dependent, right? Then that means that the enthalpy is changing as a function of temperature. Or rather, it's not linear with temperature, but rather it has some nonlinear behavior, which causes enthalpy to be non-temperature dependent. So let's think a little bit about that. Well, let's go back to the equations that we had at last module. Right, we showed that the difference of H at some temperature and the standard H is equal to some polynomial. Right, this is the Showmate equation that you guys worked on the homework. Right, when we think about enthalpy as just being a polynomial, then it's really easy to integrate it, right? If we ever have to do an integral of delta H, well, that's super easy to do, right? Because we have it right there. Well, anyone can integrate a polynomial. And we have now what we can use is the fact that the derivative of the log of the equilibrium constant with respect to temperature is equal to minus delta H over T squared. Okay, well, now all I have to do is plug in my equation. Right, so that's going to be equal to minus, right? I lose two factors of T. I get minus A over T plus B over 2 plus CT over 3 plus DT squared over 2 minus E to the T cubed plus delta H SAR over T squared. Okay, that's from this term up here. I gotta bring that over to the other side. Okay, so now that's easy to integrate, right? All I have to do is integrate this over T. Right, so the integral of the differential of log of K, which is just log of K from T naught to T.
Wait, why is DT squared over 2?
Where do you
Should be
see
over
that?
4, right? In the middle. In white.
BT squared over 2.
Should it be DT squared over 4? Does it?
Yes, sorry. Thank you. You're right. Right, is equal to the integral of minus from T naught to T of A over T prime. Again, I'm using the primes just as a dummy variable so that we don't get confused. B over 2 plus CT prime over 3 plus DT squared prime over 4 minus E over T prime cubed plus delta H naught over T prime squared dt. Well, that's about the easiest integral you'll ever do. And so what we have is that the log of the equilibrium constant at T divided by the equilibrium constant at standard conditions is equal just to a polynomial in T times some constants.
Sorry, I.
Yeah, go
just
ahead, please.
Another,
Please go ahead.
it's, well, oh, never mind, sorry.
You're good?
never mind, my
Okay.
bad.
So we have a 1/t term that gives me a log, so I'm gonna get minus a log of t. I have b/2 that gives me a term t. Or bt, sorry. Over 2. We have a t prime, so that's ct squared over 6 plus d t cubed over 12 minus 3e over t to the 4th minus 3 delta h circle over t cubed. Okay, so the point is that if I know the heat capacity with my Show-Me equation, I know delta H, I know delta S, I know delta G, and therefore I know log K. And they're all related to each other by the same expression. So if I know one, I know them all. I just want to make one more comment. This has a name, this equation. I always forget to give the name because I don't often think about the names, but I think some people, if you look them up in the books or someone mentions it, said another name. This equation is called the Van't Hoff equation. So we know the enthalpy, we know the heat capacity, we know everything we need to know about the reaction. Right? I've always been saying heat capacity defines everything about this, about the system. So everything comes back in the end to the heat capacity. The heat capacity tells you how the energy changes with respect to temperature. And so any sort of thermodynamic change induced by a change in temperature has to be proportional to the heat capacity in some way. Some might be integrals, some might be derivatives, might be divided by T, for instance. They're all dependent on CP. CP is what controls, and it's the measurable that controls all the thermodynamics. And again, remember what the physical center of that heat capacity is. It's just a measurement of how many different ways a material can store energy before it has to throw it into its bucket of excess thermal energy, which raises the temperature, the kinetic energy. And so if a system has lots of different ways to interact and to absorb energy through potential energy, different motions, different attractions, different interactions, has a very large heat capacity. But if it doesn't have a lot of ways to move, then the heat capacity is very small, because the moment you start adding energy to the system, it can't absorb it into those internal motions, and instead it puts it into kinetic energy, which is just temperature and heat. Just increases the entropy of the system. The motion. It's hot. And so KQ, right, in some sense, right, KQ, all it measures in some sense is some change in enthalpy times some change in temperature. And so equilibrium in some sense is just a measurement of how, if a process has a choice of converting molecules from one form to another, it just tells you how favorable it is to take all of that heated motion in the reactants and put it into motion in the products. If the products are much more favorable to take that energy and absorb it, and they're more than happy to take it, then the equilibrium constant is very large. The system wants to disorganize itself, and it wants to be at lowest energy possible. So if the products are much more willing to accept all of that energy that's stored as heat capacity because the products have larger heat capacities and more ways to store that energy without creating excess heat, then the energy is going to drop. And that drives everything towards that more disorganized and lower energy system. So time and time again, chemistry is lazy and disorganized. It wants to be in the lowest energy and the highest entropy. So anything that allows you to increase the amount of interactions, as well as increase the heat capacity, meaning that there's more ways to store that energy, that's a favorable process. And it drives the equilibrium forward. Okay, which is why delta H being positive or negative gives you opposite behavior for equilibrium. Because delta H tells you about the efficacy of taking excess heat or some amount of heat stored in some material and putting it in another material. And of course, if that flow is reversed, then the equilibrium is also reversed. There's a microscopic core to that, in the sense that what I'm saying effectively is that this has something to do with how much an individual molecule can store in terms of energy. And it turns out that you can calculate that number for any temperature and any molecule, right? This microscopic origin of energy really just comes down to how many different motions a molecule has to store that energy, is what this is all underlying. All of these numbers are all derived from some microscopic quantity that measures, in some sense, how much energy a molecule can store before its temperature raises by 1. And that's all equilibrium measures. So not surprisingly, all of these things are interrelated to each other by heat capacity. Okay. So, I've got 15 minutes left, and I'm trying to decide how I want to spend this last 15 minutes. Let me show you an interesting problem I want you to think about. This is a thought experiment. And this motivates us. This is going to be one of our motivators for kinetics. We'll come back and look at, in the next class, something that's dependent on temperature and pressure, more classic equilibrium problem. But I just want you to keep this in the back of your head. So I want to look at a very specific problem in organic chemistry. And I want to look at the chair conformation, which should strike fear in everybody's minds. Yes, you're going to have to draw chairs in just a second. I knew someone was going to whine. Recycle hexane. Right. I want to think about this chair. Right. So let's draw a chair. I too am not great at drawing chairs. Right, so there's one chair, right? And we know that each of these carbons, there's an axial and an equatorial hydrogen. This is what's called the equatorial. And this is called the axial. Okay, let's label one of these with a tag. All right, so let's call, for instance, this one H star. Right? We label the H equatorial. How you do that is a different question, but just imagine you can do that. Right? Well, this system is in an equilibrium with the opposite chair configuration where the hydrogens have been exchanged. Where now the equatorial hydrogen is axial, and the other one is equatorial. Now remember, it can go through a both configuration. And this is an equilibrium. Of course, it can go backwards or forwards. There's nothing really stopping us from doing it. Let me ask you this question. What's the delta G for this?
0,
Why?
because each of them are equally favored. There's no energy difference between them.
They're exactly the same. All I've done is a label. Now, typically the way we do this in experiment is we replace H with a D. So practically,
Oh yeah, so that we can track it.
right, so we can actually have a real tag that looks like a hydrogen but isn't. Right? Remember, deuterium is just hydrogen with an extra neutron. Okay, and when you change H star to D, effectively these are two different molecules, right? Now you have a D pointing up, and the other one you have a D pointing away.
Oh, and are those at different ends? Does that change?
Well, so my assumption now is I'm going to assume that it doesn't change. Okay, that they're effectively equivalent. That turns out to not be true, but the energy difference is tiny. Okay, so when you do this, we can just say that roughly, especially in the situation that we're looking at, is that this is still equal to 0, right? So of course that means that KEQ is equal to 1. So I have 50-50 axial and equatorial. All right, what I'm going to do is I want to see if I can tell with spectroscopy, if I can tell the difference between these two. All right, if I stick a deuterium here, or I stick a deuterium here, this hydrogen that's left over is in a different environment than the other. One's pointing up and the other one's pointing away. They in some sense see different environments. One thing that we know about NMR, again, maybe you don't have a lot of experience in NMR, but the idea is that if two hydrogens are equivalent, you get one peak, right? You only get one emission in your NMR. You get a different line for each unique hydrogen in your spectrum. So I'm going to put this in the NMR. And we're going to look at the hydrogen NMR. Right? And the claim is that each unique hydrogen or proton is H plus, gives a single unique signal.
But in cyclohexane, they're all the same,
Ah, great.
except if it's
Great.
deuterium, then it might.
Right. So here's the problem. Right. So here's the question. Right. So what Angie said is exactly correct. Is that if I don't tag it, all of the hydrogens are exactly the same. Right. So when I put cyclohexane in the NMR by itself, I see one line. Because all the hydrogens are exactly the same. That's our claim. Right. But remember, they're not actually all the same. Because if I cut this off, if I turn this off, and it can't equilibrate anymore, we have 6 equatorial and 6 axial. So we have 2 different types of processes. Okay, so we have 2 hypotheses, right, that are kind of contradictory. All hydrogens are equivalent. Right, so all 12 are exactly the same. We see one signal. But if all axial are equivalent,
And all equatorial,
and all equatorial are, what would we see, Angie?
then you'd see 2.
Right. At least. They'll probably split each other, but we won't worry about that. We won't worry about that. At least 2 signals. Now, what did your organic chemistry professor tell you about cyclohexane? That they're different or the same?
The same.
They're the same. Right? Because what he probably told you is that the boats chairs interconvert rapidly. That they interconvert between each other. That the cyclohexane is just constantly wagging back and forth. Okay, so what that means is that the equatorials half the time are also axial. And then the equatorials half the time are sorry, the axials half the time are equatorial, the equatorials are half the time axial. Right? So half the time they're axial, half the time they're equatorial. Right? And they swap back and forth. Well, again, half the time they're axial, half the time they're equatorial, you still think that there's two signals. Right? But they do exchange differently. So you could say, okay, maybe it all averages out and you just see one average signal. Right? You get a signal that's equatorial, a signal that's axial, but since they're 50-50, you get the average of them and it sits right in the middle. You can see one again. So the other hypothesis is that they exchange. So one is that they're all the same. They exchange rapidly. And we see one signal that is an average of two. Okay, so kind of like you might have a signal here, and you might have a signal here, and they're half there, half here. And so on average, you see it right in the middle. That kind of sense. I kind of see that. Let's go look at the experiment. So this is a classic example of taking NMR. What we're going to do is we're going to take NMR and we're going to change the temperature. Right? We know that equilibria depend on the temperature. Pressure doesn't matter here because we're taking one mole to another mole. So all the pressure dependence cancels out. So the only thing that this depends on is T. So let's go look at the temperature dependence of this spectrum. If I can find it. Aha, here it is. I'm just going to draw it. I'm going to draw as an axis and we'll do 25, 0, a big gap. It's a little big gap, minus 60 and minus 80. These are in Celsius. Okay, but you can go upstairs and take a spectrum of cyclohexane if you want. We have it upstairs. Anyone's bored one day wants to do what's that. Most boring spectrum in the world, you just get one line. We'll call it V naught is the frequency at which it emits, right in the center, and you get one line. So this is indicative of everything being exactly the same. Now, I don't know if it's that they're all the same or they're exchanging so rapidly you can't tell them apart, right? So what we need to do is maybe let's look at different temperatures and see if things change. All right, so we cool it down. To 0 Celsius. And what we find is that, again, it doesn't change, but what we do notice is very interesting that the line is a little broader than it was before. It's broadened. Here it's narrow. And then when you get down to about 60 degrees, minus 60, you find that the system, the peak no longer is sharply peaked. Let me see if I can draw it, but it kind of has a flat top to it. Like that. Strange. And as we start to go to lower and lower temperature, what we find is that broadening is not broadening at all, but it's the fact that two peaks are starting to appear and separate. So when we hit about minus 70, what we observe are two peaks that are separated at an equal distance from V naught. And then when we get to really, really low temperature, The peaks are even further apart than they were before. So we would assume here that there's one type of proton here. And here it's very clear there are two protons. Strange.
But that's also because deuterium doesn't show up,
Wow.
doesn't it?
This is also true regardless of deuterium.
Okay, okay,
This is regular cyclohexane.
okay,
Deuterium you'd actually see the same effect with deuterium, it would be much more dramatic.
okay.
I was just giving you an example of how we would do this,
Right.
this experiment. And normal cyclohexane showed. So here's the problem. We've gone from effectively one species now to two species. And so we have an equilibrium. So in some sense, we have an equilibrium between these two components. Right, but the delta G hasn't changed at all. They're still exactly the same energy. They're still just 12 hydrogens and 6 carbons, and we just flip the hydrogens. The axials are equatorial, and equatorials are hydrogen. So the equilibrium is not shifted here, right? No matter what I choose, right? Here KEQ is equal to 1. 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 But somehow the system has split into two components. All right, so what that means is that now, right, so the system is here is rapidly exchanging between axial and equatorial, right, at high temperature. And then down here, it must be the opposite, right? We've dropped the heat. The only thing the system can do is lower its entropy, right? Which means it has less heat and less ability to do stuff. So that must mean it's doing this again. There's only one thing it can do is exchange axial and equatorial. It's the only thing it can do. So nothing's changed in terms of the thermodynamics of the process. It's the exact same process, but now things are split out, right? So the only option that you have is that somehow this exchange between axial and equatorial is slowed down. So now we have what we call slow exchange. Understand that what's happening here is equilibrium. The system is exchanging between the products and the reactants at some rate.
But it's not happening rapidly.
Right. It's not happening rapidly anymore as we turn down. So what we've done here is we have a very, very rapid equilibrium. Right. What this would mean is imagine you were able to tag this. You just had axial deuterium. Right. Imagine you just had that. And then you put it in at 25 Celsius and it rapidly equilibrates and you see one line. So this is a fast equilibrium. Right. The system is going from left to right very rapidly. Right. It's going from left to right to right to left to right to right to left, right to left, very, very quickly. And down here, it's not doing that. Now it's very, very slow because it's so slow that the spectrum isn't averaging it out. You see the lefts and you see the rights. And so the only way to describe this is that the equilibrium is slow. That it's exchanging left to right extremely slowly. Very, very different behaviors. Here we have long-lasting axial up deuterium and long-lasting equatorial deuterium. They're both in the solution at the same time from our perspective. And here it looks like they're all the same. It's the same molecule. The only thing we do is change the temperature. This should tell you that we're missing something in our equilibrium calculation. KEQ tells me nothing about this behavior. But there's something else that's changing as a function of temperature besides equilibrium that's causing us to go from a system that has two components to one that has one component. And the only thing that can do that is time. We've missed a variable. We have temperature, we have pressure, we have concentration, about everything. And the only thing that we can tell now is that the thing we haven't missed is time. So something about the time at which equilibrium occurs from left to right to left is also important as well. So what we're missing here is kinetics. This is kinetic behavior. And the idea is that equilibria, chemical equilibrium, has a speed. Right? Sometimes it's slow, sometimes it's fast. So next week, we'll come back to this idea. I'm going to take a slight detour and we're going to have a fun little lecture about history and chemical engineering, about equilibrium. And then we're going to return back to this idea about kinetics and time. Okay? This is where the real meat of thermochemistry and equilibrium is really thin. All right? Have a good weekend, guys.
Thank you. Have a good weekend.
You too.
And then. But I was like, are you gonna try? I've never. I'm sorry I was late. I got invested. Problem.
And late in what?
I came in like.
Oh, I didn't notice.